This is the 21st video in a series that I'm making to support a course in elementary number theory. We just got finished talking about the order of an integer modulo n and primitive roots and when there are and are not primitive roots. And now we want to look at a nice little application of the notion of order and primitive roots, and that is the decimal expansion of a rational number that is less than 1, which obviously carries over to the decimal expansion of any rational number. You just include digits to the left of the decimal. Okay, so the first proposition that we'll look at goes like this. The rational number a over b, which is less than 1, I should say that it's also bigger than 0, has a finite decimal representation if and only if the only prime divisors of b are 2 and 5. So in other words, b has the form 2 to the r times 5 to the s. And in fact, if we're in that setup where b is of this form, we actually know how long the decimal expansion is. And it has the maximum of r and s decimal points. So in other words, a over b is equal to 0.d1, d2, d3, all the way up to d max rs, where these di's come from the set of numbers between 0 and 9. Obviously, this last one can't be 0 because then we would cut off too early. Okay, great. So let's maybe look at this proof. Notice we have an if and only if statement, so we have two things to prove. Let's start with the forward direction. So in other words, we're going to suppose that a over b, which is between 0 and 1, has a finite decimal representation. Okay, but that means that we can write a over b as 0.d1, d2, d3, all the way up to dn, and then that stops. Okay, and I want to point out that here, these dj's come from the set 0 through 9, just as kind of standard. All right, but now we're going to take this and write it with a base 10 expansion. So in other words, we're going to use the definition of our decimal expansion. So notice that this is d1 over 10 plus d2 over 10 squared plus all the way up to dn over t 10 to the n. But now we can maybe find a common denominator here. Notice the common denominator will be this largest power of 10 that is involved. That'll give us 10 to the n minus 1 times d1 plus 10 to the n minus 2 times d2 all the way up to plus dn all over 10 to the n. Okay, nice. But now we started with a over b. I guess under the hood here is that the GCD of a and b is 1, so this is in lowest terms. And we ended with a new fraction which represents a over b. Well, notice this denominator of our new fraction only has prime factors of 2 and 5. So what that means, when we do a cancellation of like terms from the numerator and the denominator will still only have factors that are 2 and 5. So that's exactly what we wanted to show for this forward direction. So let's maybe get rid of this and we'll do the reverse direction. Now we're ready to look at the reverse direction of this first proposition, and that is the only prime divisors of b are 2 and 5. So in other words, we can write b as 2 to the r times 5 to the s. And this actually splits up into two cases. I'll only do the first case because the other one is really similar. You essentially do the same kind of thing. So for the first case, we will assume that r is bigger than or equal to s. But let's notice that that means that the maximum of r and s is equal to r. So that's just going to change around which one the maximum is, giving us this result in the blue box at the bottom. Okay, so now from here, we want to take our expression a over b, which again is in lowest terms, and it's between 0 and 1, and b factors in that form up there with only 2's and 5's. And now we want to multiply it by a special version of the number 1. And that version is as follows. So we'll have a over b times 5 to the r minus s over 5 to the r minus s, like that. Okay, so let's see what that gives us. That's going to give us in the numerator 5 to the r minus s times a. And then in the denominator, well, we still have this 2 to the r. And then what happens to the power of 5? Notice it's 5 to the r minus s plus s. In other words, it is 5 to the r. Great. So in the end, we have this looks like 5 to the r minus s times a over 10 to the r. Okay, so the next thing that we want to do is take this thing which I've boxed in pink and write it with a base 10 expansion. In other words, write it as a linear combination of the number 1, the number 10, the number 100, so on and so forth. So we know base 10 expansions are unique and they're always possible. So that allows us to write this whole thing as a naught plus 10 times a1 plus 10 squared times a2 all the way up to 10 to the m times am. And this is all over our 10 to the r term. And now here we know that all of these ai's come from the set 0 through 9. Okay, another thing that we know immediately is that r is bigger than m. And we know that because our original number a over b is less than 1. Okay, so let's see how this turns into a decimal expansion. Maybe we'll do this division by 10 to the r for all of these. That'll give us 10 to the minus r times a naught plus 10 to the minus r plus 1 times a1 plus 10 to the minus r plus 2 times a2 plus all the way up to 10 to the minus r plus m times am. Great. And then next, I'm going to add on a bunch of zeros. And how many zeros will I add on? Well, I'm going to add on until I get to the AR term. So next, I'll have 10 to the minus r plus m plus 1 times 0 plus all the way up to 10 to the minus 1 times 0. Okay, great. But now this is exactly the reverse expansion of what we would write down as a decimal. So this is equal to 0.000. Well, there's a bunch of zeros. How many are there? So there's 1 from this 10 to the minus 1 all the way up to, let's see, that's r minus m minus 1. So just to reiterate, there are r minus m minus 1 zeros right there. And then we start picking up at the non-zero terms. So we have a sub m minus 1, all the way down to a sub 0. And then it stops. That's a terminating decimal. So now it's worth to point out that here we have exactly m plus 1 digits. We're going from 0 to m, but putting this all together, we have r digits, which not only finishes this reverse direction, we have a finite decimal representation, but it also proves this little blue box here. Okay, so let's maybe get rid of this and we're going to keep doing a couple more results like this. Okay, so our next theorem is a big one. It's one that you learn maybe in elementary school, and that is that x is a rational number if and only if its decimal representation is finite or eventually periodic. So in other words, it will terminate or repeat. And that's maybe the first distinguishing characteristic between rational numbers and irrational numbers that you learn, is that irrational numbers are non-terminating, non-repeating decimals. Okay, great. So I want to point out that all along this proof, we're going to take x between 0 and 1. So notice that we could just take an arbitrary value of x, which is a rational number, or maybe any real number, and move it to the interval 0 to 1 just by adding an integer. So that's really no big deal. Okay, so our proof is again an if and only if statement. So we'll start with the reverse direction first. Okay, so that means we want to assume that our decimal representation is finite or eventually periodic. So we'll in fact assume that it's eventually periodic, but that's really a more general case of finite, which we'll talk through after we write it down. Okay, so let's assume that x has the form 0.d1 all the way up to dm, and then p1 all the way up to pn, and then this repeats. So I'll use the notation where we have a bar over this to mean that this repeats. Okay, now I want to point out that this could be turned into a finite representation if all of these are equal to 0. Then it just repeats with all zeros and we're good to go here. And we have a finite decimal representation. Okay, so now we'll take this object and start forming it into a rational number. So let's see, this means that we can write x as 0.d1 all the way up to dm plus 0.00. How many zeros are there? Well, there are exactly m zeros, and then we have p1 up to pn, and I'll put a bar over it to mean that it's repeating. Okay, so what have I done? So I've broken x into the finite part and then the repeating part. Okay, so from our first result of the day, we know immediately that this is a rational number. So in fact, if we write it as a rational number, its denominator is only divisible by 2 and 5, again, by the proof of what we just showed. So we really just have to worry about this thing right here. So now let's write that down. So now we'll just consider this object right here, which maybe I'll call y, which is equal to 0.000, and then p1 up to pn, and then this is repeating at the end. And just to reiterate, there are m zeros here behind the decimal. So I've got m zeros right there. Okay, now I'll take this and I'll rewrite it as a sum of rational numbers. It's going to be an infinite sum, but that's okay. So maybe let's note that we have y is equal to p1 over some power of 10. What power of 10? Well, it's going to be the m plus first power of 10, just to encode all of these m zeros. So we've got 10 to the m plus 1. And then next we'll have plus p2, 10 to the m plus 2, all the way up to pn over 10 to the m plus n, like that. But this repeats, so that means the next term will be another p1. So I'll put that right under here. We'll have this as p1 over 10 to the m plus n plus 1. And then, like I said, it keeps repeating. We have p2 over 10 to the m plus n plus 2, plus all the way up to pn over 10 to the m plus 2n. Okay, nice. Then it's going to start repeating again. So the next term will be p1 over 10 to the m plus 2n plus 1 plus p2 over 10 to the m plus 2n plus 2 all the way up to pn over 10 to the m plus 3n. And then that repetition is going to keep going. So what I'll do from here is just sum each of these columns. So notice each of these columns has a common factor that can be factored out. And that common factor in the case of the first column is p1 over 10 to the m plus 1. In the second column, it's p2 over 10 to the m plus 2, and then so on and so forth. So that means I can write my y as p1 over 10 to the m plus 1. Then what I have left is 1 from this term plus 1 over 10 to the n from this term plus 1 over 10 to the 2n from this term, but then that keeps going infinitely on. I guess I should put that these are summing infinitely down that way. Then I've got something similar for the next term and the next term and the next term. So I'll just put plus dot, 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 and then my last one will be pn over 10 to the m plus n. And then I'll have 1 plus 1 over 10 to the n plus 1 over 10 to the 2n plus dot, dot, dot. Like that. Okay, nice. But now the important thing to notice is that each of these is a geometric series. And since each of these is a geometric series, we can use the standard formula for the sum of a geometric series to find a closed form. So that means we have y1 over 10 to the m plus 1. Then this guy right here sums up to 1 over 1 minus the common ratio. So that's going to be 1 over 1 minus the common ratio is 1 over 10 to the n here. But then that's happening for all of these terms. So that happens for the next one, which is the P2 term, all the way up to the Pn term. So we have Pn over 10 to the m plus n, and then 1 over 1 minus 1 over 10 to the n, like that. But let's see what we've got. This guy right here is obviously a rational number. This guy right here is obviously also a rational number. All of these are rational numbers. We're adding up finitely many rational numbers at this point, which means in the end, we get a rational number. So put that together with the fact that the part that we trimmed off was also a rational number, tells us that our x, which we started with as a finite or eventually periodic decimal, is in fact a rational number. So that finishes the proof of this reverse direction. Okay, so now let's look at the proof of the forward direction. Okay, so now let's look at the forward direction. So we want to suppose that x is a rational number. We're still keeping this assumption right here that x is between 0 and 1, just kind of for ease of use. So that means that we can write x as a over b, where those are some integers. We can actually take them both to be positive integers, and b is larger than a, but I won't really encode that into this. Okay, so now we want to consider the following set of numbers. So that set of numbers will depend on this numerator right here. So we'll have a, and then 10a, and then 10 squared a, and then 10 cubed a, so on and so forth. So in other words, we're going to have 10 to the k times a, as k runs through all non-negative integers. So notice this set is most definitely infinite because there are infinitely many non-negative integers. But there are only b residues modulo b. Well, I mean, that holds for any natural number, and b can be taken to be a natural number, so we're good to go there. There are only b residues mod b, or in other words, there are only b possible remainders when you divide something by b. So what we'll do is reduce everything in this set mod b. But given that this set has infinitely many elements, but there are only b possible residues, there must be 2 elements in this set that are congruent mod b. So let's write that out. So by those words that I just said verbally, there exists m greater than n greater than or equal to 0, such that 10 to the m times a is congruent to 10 to the n times a modulo b. And I guess I should say that this is the minimum distance between m and n, but we won't really worry about that so much. Okay, so from here we can use the definition of congruence mod b to say that this means that b divides 10 to the m minus 10 to the n times a. I just factored an a out of that. But that's the same thing as saying that 10 to the m times a minus 10 to the n times a over b is an integer. But being an integer means your fractional part is 0. Let's recall that the notation for fractional part is these curly brackets. So here we have, that means that the fractional part of 10 to the m a minus 10 to the n a over b is equal to 0. So again, just to reiterate, the fractional part of, say, a number z is equal to z minus the floor of z. So it's the number minus the integer part. Okay. But now if the difference of these two numbers has no fractional part, that means they individually have the same fractional part. So in other words, we have the fractional part of 10 to the m times a over b is equal to the fractional part of 10 to the n times a over b. Now that we've got that taken care of, let's go ahead and write the decimal expansion of a over b, as it'll be useful for the next steps. I can write that as 0.d1, d2, d3, and then that goes on forever. Obviously, we can assume that it goes on forever because if it doesn't go on forever, then it terminates after finitely many spots. But then we already proved in the last proposition that means it is a rational number. It's a special type of rational number. Okay, also we have this more general statement, which is the fractional part of 10 to the k times a over b, where k is any non-negative integer, is equal to 0 point d sub k plus 1, d sub k plus 2, d sub k plus 3, and then so on and so forth. And why is that? That's because we're moving k of these things from the right-hand side of the decimal point to the left-hand side of the decimal point. But when we calculate the fractional part, that means it's going to disappear. Okay, so now we can take this expression for a over b as a decimal expansion, and then this little fact that we just noticed, and plug them into this equation involving the fractional parts of these two objects and see what we have. So that tells us that 0 point dm plus 1 dm plus 2 ... is equal to 0 point dn plus 1 dn plus 2. But then keeping in mind that n is less than m, that means eventually we will find dm as we go further into the expansion. But after that is dm plus 1 dm plus 2, and then we keep going. But now look, we've got two decimals that are the same, but that's setting up our repetition. And that's because we've got this m plus first, m plus second term, and so on and so forth, which starts getting repeated over here after all of these terms. So that's what we have going on right here. This guy right here just keeps being repeated and repeated and repeated. So that sets up a period with which length? The length is going to be m minus n. So how would we carefully find that m minus n? Well, it will be the first place where we get this type of congruence. Okay, so let's clean up the board, and I'm going to present a corollary to these last couple of results along with some terminology. Okay, now we're ready to put together the results that we've seen so far into a nice package. But first, a little bit of terminology. So if we've got a rational number between 0 and 1 with the following decimal expansion, so it's 0 point d1, d2 up to dm, and then it starts repeating dm plus 1 to dm plus n, and that repeats on and on and on. So this bit, which I've underlined in yellow, is called the pre-period, and we would say that this is pre-periodic of length m because there are m digits there. And then notice we've got n digits which are repeating, so we would say the length of the period is n. Okay, so now we've got a final proposition, which is really a corollary of these other things that we've seen. And that is the decimal expansion of this rational number a over 2 to the r times 5 to the s times b, where we have these GCD requirements. So notice the GCD of a and 10 is 1, the GCD of a and b is 1. That just means that this is in lowest terms. And then the GCD of b and 10 is also 1. That means we factored every factor of 2 and 5 out of the denominator already. So this type of rational number has a pre-period of length maximum rs. So the maximum power among the power of 2 and the power of 5. So that actually follows exactly from the proof that we saw at the very beginning of the video. We actually outlined that already, so we're not going to worry about that proof. Then the second thing, which will be built off of the proof that we saw of the last theorem, is that the period of this is length order mod b of 10. Okay, so let's maybe firm up the proof of this second thing. Okay, so from the previous proof, we have a period of n if we had 10 to the m times a was congruent to 10 to the m plus n times a modulo b. So that's just a step which has been plucked out of the last proof. And I should say here, n is the smallest such that that happens. Okay, but now we can move some things around. So notice that a and b are relatively prime, so we can cancel them from both sides. 10 and b are relatively prime, so we can do cancellation there on both sides as well. And that will leave us with 10 to the n is congruent to 1 modulo b. Okay, but notice we've got 10 to the n is congruent to 1 mod b, and n is the smallest number that makes that occur. And n is also the period. But notice that we've set this up exactly. This smallest number such that this kind of thing occurs is exactly the order. So we have n is equal to the order mod b of 10. Okay, so that finishes the proof of this second little thing. Okay, so let's maybe finish this video off with one example. Okay, so let's finish with a little example and then a warm-up exercise that builds off of this stuff. So let's find the pre-periodic length and the length of the period for the following rational number. So we've got 43 over 140. So the first thing that we want to do is write 140 in a factored form using powers of 2 and 5. So notice that this is equal to 2 squared times 5 times 7. So from this, we can immediately see that the pre-period has length maximum of 2 and 1, given that 5 is equal to 5 to the first power. So like I said, the maximum of those is obviously equal to 2. Then, in order to find the periodic length, we're worried about this number that's left over, and the order of 10 mod that. So in other words, the length of the period will be equal to the order mod 7 of 10. So in other words, the smallest number, so that when we raise 10 to that number, we get 1 mod 7. But notice that we can reduce 10 mod 7 to 3, so that's going to be the same thing as the order of 3 mod 7. Now, I won't work that out because we've spent a bunch of videos and probably a bunch of class time working out the order of an integer mod n. I'll just say that this is equal to 6. In fact, 3 is a primitive root mod 7. Okay, then maybe to finish this example off, we could maybe check that this works by looking at the decimal expansion of this. And in fact, we have 43 over 140 has5 decimal expansion. So we have 0.30714285, and then that repeats. So we've got a pre-period of length 2, and then it's periodic of length 6. And then as maybe a nice warm-up exercise, let's do the same kind of thing for these two rational numbers, 9 over 35 and 15 over 112. And that's a good place to stop.